the people at 0xPark have this list. It's a running list of all the exploits that have been found so far in all the major ZK protocols. As you can see, the list is already lengthy, and you have to realize that this whole technology, ZK, is barely even in production yet. And we already have pretty much every major protocol on the owned list. The same list also specifies a few different kinds of bugs that are reoccurring over and over again. And besides bugs that are down to the actual protocol, so for example, we've done something wrong with trusted setup, we've leaked something, etc., the majority of them are actually bugs in arithmetic circuits. So they are bugs in the way we've implemented the logic of the protocol. So now the question is, how does it happen? Why is this whole thing so difficult? And to start with, to start answering that question, let's look at a model of what happens with our computation in an actual ZK protocol. So this process is usually actually a two-step process, where we start with the public inputs and the private inputs to our circuit. And then we have something that's called a witness generator. And the witness generator takes the inputs and essentially generates some more data that we will then be committing to. And then it's fed to a prover that uses a constraint system to actually generate the proof. And the way this is done in practice is that we use DSLs that compile simultaneously to both of these programs. So if you are using something like CIRCOM or Halo 2 or GNARC, your program compiles both to a witness generator and to a constraint system. And I'm going to show you that those two are very different programs and very different programming models that we unfortunately try to smoosh into one single program. And that's the source of many issues. So let's look at the two different programming models. We have the witness generator, and witness generator is nice. It's standard programming. It's what we know and what we know how to do. It takes an input, it produces an output. It's also very easily testable because it's just a standard program. So I can do some example inputs, I can use fuzzing, I can use unit testing, easily testable. So great news, right? Except it's completely irrelevant for the security of this system. Witness generator, from the perspective of an attacker, may not even exist. They are never interacting with it. They do not care at all that something is there. So all of our security assumptions are down to the security of the constraint system that we have generated. And the constraint system is a mathematical description. It's a set of equations that tell us something about a set of numbers. So we have some inputs, some outputs, we have some equations constraining them, and all of those equations happen over a prime field. Now, this is very difficult to reason about because it's not a program. It's not something that takes inputs and produces outputs. It's something that takes both inputs and outputs and then smooshes them together and gives us a Boolean. It says yes or no, it passed or it failed. And it's the only part that is cryptographically relevant. So when we are talking about security, this is the part that we want to work with. This is the part that we currently have very little idea of how do we actually test it and how do we make sure that this is correct. So let's look at an example. The task at hand is we have a number and we want to compute the binary representation of this number. The witness generator part is what any programmer in this room would do, right? We just use some bitwise operations, and we take the if bit, and we say that the if output of my circuit is the if bit of the input. In the constraint system, which, again, is the only part that matters, that's just a bunch of equations, a bunch of multiplications constrained by equalities. So what I'm saying is that every single output multiplied by every single output minus 1 is 0. And I'm saying that if I dot product the output with a vector of powers of 2, that's going to be equal to the input. Now forget about the witness generator, because the attacker forgets about the witness generator and tries to exploit this. Question is this a good implementation of a binary representation of a number? So we have the first constraints. They essentially state that every single output needs to be a bit. It needs to be a 0 or a 1. And we know that when we recover the number from this binary representation, it is equal to the input. So it looks like a good binary representation, but it's, for example, it may not be unique. So when is it unique? Turns out that this is only unique if n is less than the prime field's bit length minus 1. And this is completely not obvious. Like it's not something that you can see at first glance. It's a mathematical property that you have to come up with. And if you try to depend on this being a good binary representation always in your circuits, in terms of being unique, you may fail. I have actually failed in this way, which is why this slide is here. Moreover, everything is happening in a prime field. So this is modular arithmetic. And as developers, we are used to modular arithmetic modulo a power of 2. Modular arithmetic modulo a prime is kind of weird. We only have addition and multiplication. We have no natural way to think of in terms of bits. We have no natural ways to do modulo operations or to do comparisons. Everything is unordered. It's this like very uniform bag of numbers. But we want those things because most protocols actually need to know, like, if my balance is greater than 0. This is a very good question to ask, right? So we need to simulate all of those operations using tricks like the one I've shown you just before. And this simulation is, first of all, difficult, but second of all, it's also costly. And because it's costly and provers are very slow, what do? We start golfing. We start dropping assumptions. And now it gets even more interesting because even if I did everything correctly and by the book, it would already be quite dangerous. Now I'm also trying to optimize this, and I'm saying, oh, maybe I don't need this constraint because it's going to be fine because whatever, right? So how do we deal with this situation? How do we actually prove that everything we've done so far is correct? And let's start with an obvious point that we may have here, which is, can we even monitor these systems? Let's say I wrote a ZK protocol and I've deployed it to mainnet and it's happily running and I'm monitoring it. I want to see if I'm being hacked. The very semantics of ZK protocols is that I know a set of inputs such that your program says, yeah, okay, this is fine, let's proceed. What does this mean? This means I don't actually know the inputs to my system. I have something deployed on mainnet and people are using it and the system is doing something and I don't exactly know what it is doing. So we won't even know that we are being owned. If I know a way to, for example, generate false proofs for Tornado Cache, you will never know. If I'm smart about it, right? And I don't start caching out everything at once. If I do it slowly, the worst thing that happens is some users are going to complain on Twitter saying that they are being hacked. There isn't even a way to verify that I'm doing this. So this is more dire than what we deal with in traditional DeFi. Even though it's not great in traditional DeFi, this is even worse because we won't even know that we are being hacked. So what can we do? Can we do testing? We can do testing for the optimistic paths, but it's very difficult to say that my predicate, so my circuit, my constraint system, doesn't admit inputs that don't have this property. It's not something that we can test for. It's also not something that we can fuzz for, because fuzzing would be very, very unlikely to find the inputs that break the system. So this is mostly a dead end. We can test the happy optimistic paths. We can use our witness generator to do testing, but anything beyond that is beyond our reach. We also have some static analysis tools, and those are good actually. Use the static analysis tools. So there are some tools developed by 0xPark and by the people at Veridice. So there is ECNI, there is Picus. Those are systems that are very automated in that you just pass them the circuit description and they will output some information. So they will say that, for example, you are lacking some constraints. They will say that some input is unconstrained. It could be anything. They will tell you that there is no functional relationship between the input and the output, right? So that means that your circuit can accept multiple outputs for the same input. Now, one thing to keep in mind is that this is not necessarily a problem. For some circuits, that's a desirable property, and we want that. But this is very helpful for the common case. Unfortunately, it's not enough to like ensure security of all those systems, which leads us to our work, which is formal verification. So with formal verification, what we can do is we can compile the circuit to a theorem prover, which is like a special programming language that allows you to actually prove things about itself. We can model what the circuit does in terms of the constraints, and we can prove pretty much anything about the protocol. Now, this unfortunately has some dev overhead, so it's not a free tool, right? It's not something that you can just run and then boom, you get correctness. This is something that you actually have to spend time writing. The tool itself is free, but the time you are putting into using it is absolutely not. So our solution for GNARC, you have this pretty QR code that you can scan and go to our GitHub. This is an extractor for NARC, which is one of the DSLs for writing those circuits. This compiles to Lean4, which is a theorem prover developed by Microsoft, one of the leading in the field. And you can prove anything about the circuits you have created with NARC. What do I mean by you can prove anything? Let's do a quick case study of the semaphore protocol. For those of you who don't know, this is like one of the most common protocols in ZK. It maintains a set of people that are allowed to perform certain actions. It allows them to perform those actions and say that, and also allows us to verify that those actions are unique. Like any person that is allowed to do the action may only perform the action at most once. So we have an implementation for this. And now what can we prove about it? So theorem number one that you will find in the GitHub repository is for any set of parameters, if the identity commitment, so the user is in the Merkle tree, we can generate a valid proof. So this already testifies that there is no protocol level censorship other than the whitelisting in the Merkle tree. Another thing that can be proven is that for any set of parameters, if my constraint system says yes, that means that the user is already allowed to perform the action. So no unauthorized user will ever enter the system. And you can see that the statements in Lean4, the statement of these exact theorems in more mathematical language. And you can see the proofs for yourself in the GitHub repository. And the last thing we can prove, well, we can prove many more things, but the last one that I have on a slide is that if the same user tries to signal twice, I will know. There is a unique identifier that I can compare and say, I know you are trying to signal twice, please don't do that. So what can we prove? We can prove the exact semantic properties of the protocol. So it's not even testing a program or testing a constraint system. At this level, I'm proving things about the protocol I've designed and the implementation of the protocol in the particular proving system. And that is all. Thank you. If you have any questions, please let me know.